Hey, guess what we're going to cover in this lesson? Instantaneous rates of change, the derivative, all the things that we've been working on all year long up to this point in time. And if you'll remember, way back at the very beginning of the year, we talked first about finding the slope of two lines. Well, that's just what we have right here. We've got these two slopes. And notice, if you look up here on top, this is the, let's get a little bit darker color than that. On the top, this is the change in y, and on the bottom we have the change in x. And so when we're working with these guys, that's all we're doing. As it turns out, this is the slope of a tangent line, and hey, as it turns out, this is also a derivative, which you might see in several different ways. So here's all these ways you might see a derivative. Well, what does that mean for you? That means that we can find instantaneous rates of change. You don't need to see my Dropbox folder, so let's get that off there. You can do any instantaneous rates of change by just simply finding derivatives. So let's say that we've got some random circle, okay, some random thing. Find the rate of change in the area of a circle with respect to its radius r. So what does that mean? Well, that means that a is equal to pi r squared. Okay, that's the radius of a circle. And so now it wants to find the instantaneous rate of a circle. We can do the really cool limit rule here and just have a super great time with that. Or we can follow some of our derivative rules that we just learned and we're dying to practice with. So what we would simply say is, for this guy, find the rate of change in the area of a circle with respect to its radius. We would say that if we've got a equals pi r squared, then dA dr, the rate of change of the area over the rate of change of the radius. And then we just take our exponent 2 times the number in front. In this case, pi is a number, and then subtract 1 from the exponent on the r. So 2 minus 1 is r, and hey, guess what? Here is our instantaneous rate of change. Well, then it says evaluate the rate of change when a is 5 and r is 10. Hey, that's really not a problem. The rate of change then just simply means that wherever we see r, we're going to put a 5 in. So I'll just work that guy out in this kind of mustard color here. So we would say that dA dr equals 2 times pi times 5, or 10 pi. And 10 pi is a perfectly legitimate answer. There's no need to do anything else to that. It's totally fine. We could also investigate what happens when r is 10. So dA dr is going to be 2 times pi times 10, which is 20 pi. And again, this is a legitimate, real life, totally cool answer. There's no need to go throwing decimals around when it's just not necessary. So that's what these guys would look like. And so then the last question is, if r is measured in inches and a is measured in square inches, what units would be appropriate? And so in this case, then we have to really pay attention to what's going on. First off, we're told that r is measured in inches. The r is on the bottom, and then we're told that the a is measured in square inches. That's on the top. So it would be appropriate in this case to talk about inches squared per inch. Now, I know this reduces, but when you're working with a derivative, you just simply leave your units alone and don't mess with it too much at all. So area would be, or the derivative would be, inches squared per inch. Okay, so here's just a real quick rate of change problem using some of those derivative rules, and that's why we really like it. Alright, here we go with one of those dadgum informational slides. There's not a lot of math on this slide, but a lot of things that you need to understand as you work through the different ways that instantaneous velocity and derivatives work in real life. Okay, so one of the things that we can get from all of this is what's called displacement, and it's the first term listed here. It's the change in position of an object over an interval of time. Okay, so just how the object changes its position. We don't know how it's going to change it or where it's going to change it to. We just know that it's not going to be in the same place from where it started. Okay, so if the position function is f of t, and position is usually shown with this letter S, so anytime you see that letter S, we're talking about position. Okay, then the displacement over over some time interval from t to t plus delta t. Now remember, this just represents a stopping point, so this is where I would stop, t plus delta t. This is where I would start. So gosh, all of a sudden all this looks familiar. Is going to be our change in position. So displacement is where the time you stop minus the time you start over the entire travel time. Okay, and that's the function for the time you stop. So when we look at this guy, the function where we stop minus the function where we start all over your change in time. It's exactly what we've been doing all year. It just looks different because the letters are different. The process is the exact same thing. So don't worry the small stuff on that one. You've seen it before a lot of times. Let me just put a parenthesis in here. Instantaneous velocity then is the derivative of position. So if we said that position, if we're talking about position is this S guy right here, this is position, then velocity is the derivative of that. So S prime is going to be my velocity. And oh, by the way, this guy right here looks an awful lot like this guy up here, just no limit. Okay, so we've worked with both of these several times. So anytime we want to know the instantaneous velocity of anything at a specific time, just take the derivative of the position function. When you take the derivative of the position function, you've got that instantaneous speed. Okay, the next one is the speed, and speed is a little bit tricky. It's just absolute value of the velocity function. So once you've taken that derivative, remember your instantaneous velocity could be negative 50 miles an hour. We could go backwards 50 miles an hour. Well, what was our actual speed? 50 miles an hour. Even though we were in reverse, it's like when you drive in your car, the speedometer only shows positive rates of change, positive speeds. And so even when you're backing up, your car would still quite possibly tell you, hey, you're going 20 miles an hour. It wouldn't say negative 25 miles an hour. So when you're doing that, the speed is just absolute value of velocity. All right. Last thing is acceleration. So acceleration is the derivative of the velocity. So if my position function is s, okay, this is position, and if s prime is velocity, then s double prime, which is equal to v prime, will be equal to my acceleration. So when you're asked to find the acceleration of an object, take two derivatives. If they give you a velocity and asked to find the acceleration of an object, take a single derivative. So all of these things are related, and we'll actually talk a little bit about the third derivative, but I don't know if we talk about that third derivative in this particular section. So I think we're good on that stuff for now. So start with position. Apply a derivative, have velocity. Take absolute value of velocity, you have speed. Take derivative of velocity, you have acceleration. Three very important things, and if you're taking physics, those things also come into play quite a bit. Okay? Information slide here. We're going to practice what we've just looked at with the next example. All right, so let's really check out rates of change and velocity and look at acceleration and all kinds of like really cool things here. So we're going to sum it all up with one big physics problem, a baby physics problem, not a hard one. Like if you want a really hard physics problem, go get an AP Physics. I don't know what goes on in there half the time, but some of these things that we're going to talk about you will use. So a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of s equals 160 t minus 16 t squared. It's after t seconds. So what they've given us right off the bat here is the position function. Do you see it? Right here. Here's my position. Bam, right there. So the first question is, how high does the rock go? Okay, how high does the rock go? Well, let's just run through a real quick super rough sketch and see if maybe calculus won't help us to solve this. So here we've got this rock. Dynamite blows it up. It follows an upside down parabola and it does like this. So what I'm interested in is this point right here. This is my maximum height. Where does that happen? It happens when you have a horizontal asymptote. And how do you have that horizontal asymptote? When your slope is equal to 0. And how do you find where your slope is equal to 0? Take the derivative of the position function, set it equal to 0, find the time. So this problem, which looked really nasty to start with, how high does the rock go? We're just looking for a horizontal tangent line. So S prime is going to be equal to 160 minus 32t. And that's going to be the equation to find the slope of any tangent line for this graph. I'm really interested in where my tangent line has a slope of 0. So what I'm going to do is I'm going to put a 0 in here, and I'm going to solve this guy out. Equals 160 minus 32t. Sorry about the change in color. Get it back to the right one. So what do? I simply subtract 32 from both sides, and then divide both sides by that 32. So t is equal to 160 over 32, and if I double check that with my calculator, that's going to be 5 seconds. Okay, in 5 seconds, that's when I get that horizontal tangent line, or my maximum height. How cool is that? You couldn't do that in pre-calculus, and that's why this is fun. Okay, so what is the velocity and speed of the rock when it's 256 feet above the ground on the way up and on the way down? So again, now we're wanting to know, okay, if we go back up here to this graph, I want to know, when is my height equal to 256 feet up and down? So I'm going to take my position equation, 160 t minus 16t squared equals 256, because that's the question, where does my position equal 256 feet above? And I'm going to move everything to the right, because as I work with this equation, I like to have a positive leading coefficient, and that leading coefficient in this case is this guy right here. So when I move him over to the right, what I end up with is 16t squared minus 160t plus 256 equals 0. And if I want to find how long it takes for the rock to get up to that height, what I have to do is actually solve this out for t. Now, this problem actually foils out, and that's really, really great for us. But if it didn't, you could use the quadratic formula to solve it out. First off, though, you can pull out a 16 from all three pieces. So that's going to give you a t squared minus 10t. And then 256 divided by 16 is 16. And we can actually divide both sides by 16 so that it goes away. 0 divided by anything is 0. So that leaves me with t squared minus 10t plus 16 equals 0. And then when this factors, I'll come over one more time, when this factors, we're going to just set whatever we get our factors to equal to 0. So what times what is 16 that adds up to, and we know it adds because of this guy right here, that adds up to negative 10. So it's got to be minus 8 minus 2. And so you set those guys equal to 0, and these are the two times that you get. It's going to be 2 and 8. So when is the speed of, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? Well, that's at times of 8 and 2. So what do I do to finish this problem off? I come back over here to my equation for derivative. Let's just go ahead and write it again real bold where we can all see it. The derivative is 160 minus 32t. Okay, so once I get that part, then I just need to stick in 8 and 2 for t and do my math. So I've got a little bit of space right here, so I'm going to do both of these right up here. So what I'm looking at is the velocity function at 8. And remember, s prime is velocity with respect to time. So the velocity at 8 seconds. So what is the velocity at 8 seconds? Well, it's 160 minus 32 times 8. And when I do that math, I end up with negative 96 feet per second. And I'm cheating. I'm looking at my calculator over here off to the side. And then how do I find my velocity at 2? I just simply stick 2 into my m for t. And when you punch that into your calculator, you're going to get 96 feet per second. So I have to use my derivative to figure out what my instantaneous velocity is, but I've got to use some of my algebra too to figure out at what values of t I'm particularly interested in. Well, what is the acceleration of the rocket at any time during its flight? Remember that we start with position. We start with position, which is 160t minus 16t squared. Then we go to velocity, which is the derivative of position, which is 160 minus 32t. Then we go to acceleration, which is the derivative of velocity, which is the second derivative of position, which is going to be negative 32. And negative 32 what? Well, the correct units on this are going to be feet per second squared, or per second, as some of you guys have may say. So this has an acceleration that's continually slowing it down. It is not speeding up at all. So when does the rock hit the ground? Well, that's a really good question. The rock hits the ground at the two places that it crosses the x-axis. So we're back to that original function then. We just need to set 160t minus 16t squared equal to 0. So what I would take is, I want to know where my position is equal to 0, because that's where we're hitting the ground. And you'll notice there's a t in both places here, so I'm just going to factor a t out. And then we set both terms equal to 0, so t equals 0. Well, we knew that. We had to launch the rock from the ground with the dynamite anyway. And the other part then is 160 minus 16t equals 0. Well, what do you get here? You're going to end up with 160 equals 16t. So when t equals 10 seconds, you're going to cross back over and hit the ground. And I'm just double checking on my calculator here, and that's what it is, 0 and 10. So a really, really involved problem. Don't hesitate that if you have a question on something with this particular problem, that you note it and write it down and tweet me or ask. Also, if you may need to rewind a couple parts a couple of times. There's a lot going on in this problem, but it's a really, really good problem. Okay? Okay, back to the informational slide, and if you need to pause and find your notes, do that. I'll give you 1 second. Okay, so what we're going to talk about now is looking at a particle moving along a line, and they give us a position function, but with this position function, one of the rules is that t has to be positive, and they show us what that position function is, and they want to know, all the answer to all these questions. So find the displacement of the particle during the first 2 seconds. Well, when you're looking at displacement, don't forget, displacement is the change in position, which is the place where you stop minus the place where you start. So in this case, we're stopping at 2 seconds and we started at 0 seconds. And we have the position equation here. So all we have to do is look at stop minus start. That's it. That's all we need. So when I do that, and I'll do the stop with red. How about that? Okay. So when I do my stop, I'm going to have 2 squared minus 4 times 2 plus 3 minus my start. So minus, and then my start needs to be everything in green. I'll put everything in green here. So my start is all this, and minus the entire start, not just part of it. Well, that's going to be 0 squared minus 4 times 0 plus 3. So basically what I'm going to end up here with is 4. Let's see, how about let's undo that and do it in red. So I'm going to have 4 minus 8 plus 3 minus 3. Okay, and so when I get done with all of that, what am I going to be? I'm going to be at minus 4. Well, minus 4, what's that mean? That means that we're going to be 4 units to the left of our starting position. 4 units to the left of our starting position. That's all it means. Negative means left, positive means right. We're going to keep it simple. Okay, so find the average velocity of the particle during the first 4 seconds. Well, gosh, average velocity, what was that? That was velocity, instantaneous velocity, is not quite what we're ready for here yet, because they want to know the average over during while the first 4 seconds is taking place. So what does that mean? That means that again we're going to have a function that looks like the change in position, okay, divided by the change in time. So delta S over delta T. What does that mean? That means that we started, it's all about stop and start. It's our position where we stop minus our position where we start, okay, and our change in time. Where did we stop with time? We stopped at 4 seconds. Where did we start with time? We started at 0 seconds. We want to know over the entire first 4 seconds what's the average. Okay, so back over here to my position function. I stop at 4, so again we'll go with red here. That's going to be 4 squared minus 4 times 4 plus 3 minus, and then we'll do in green my starting position, so green, and that's going to be 0 squared minus 4 times 0 plus 3 all over where I stopped, which was 4, minus where I started, which was 0. So we're going to work out all of this and see what happens. And as it turns out, let's see, I know that my 3's go away because I've got a negative 3 here and a positive 3 here. That goes away, and I'm going to end up with 16 minus 16 over 4, which is a big fat 0. And what are we working with? Meters and seconds. So what's my average velocity? 0 meters per second. Well, what's the instantaneous velocity of the particle when t is equal to 4? Now, this is where it gets interesting, because my average over the entire first 4 seconds was 0. Basically, I have a velocity of not moving on average. Okay, so what about instantaneous? What's going on when t is equal to 4? When t is equal to 4, what's my speed? What's my velocity? Well, let's just look at position here. We've got position. Let's go ahead and find the derivative of position, which is the same thing as my velocity. And so what I'm going to end up with is 2t minus 4. So find the instantaneous velocity of the particle. I want to know then v of 4. What does that mean? That means everywhere I see a t, I plug a 4 in. So I'm going to have 2 times 4 minus 4. That's going to be 8 minus 4, which is 4 meters per second. 4 meters per second. That's my instantaneous velocity. Okay? Notice it's different than my average velocity. I'm looking at an average velocity from 0 to 4. Now I'm looking at instantaneous velocity, this little tiny snapshot of time. Okay? And so that's why those numbers are so different, and they are different amounts. Okay? 4 seconds, instantaneous. They're different. Okay? Find the acceleration of the particle when t equals 4. So let's go back over here to our particle again equation. And if I look at the second derivative, I'm going to get 2. That's the same thing as your acceleration at any point in time for this particular problem. So when I punch this guy in, I'm looking at 2. So it doesn't matter what I am out of variables. So when it asks a of 4 and there is no 4, all I can do is write in 2 meters per second squared. That's it. If there was a t in there, I'd plug a 4 in, but I don't have one of those. Okay. Describe the motion of the particle. At what value of t does the particle change directions? So now this is kind of a tricky little deal. What's going on? Think about your instantaneous velocity. Well, let's sketch a rough graph of this guy. And basically what we have, and this is not going to be 100% exact, okay? This is a rough sketch for informational and educational purposes only. We're going to have some sort of something that looks like this. Okay? I take that back. It's going to look like this. Okay? I don't know exactly where that vertex is going to be, but I know it's a parabola opening up and it's not on the origin. So the things that are important to note here, until I get to my vertex, as I move in this way, my velocity is decreasing. And as I move this way, my velocity is increasing. Okay, so what's going on with this particle then? Like, how do we describe all of that? And so again, and we want the parts that are actually going to be greater than 0. So what we do is we're going to take that derivative, 2t minus 4, and let's just set it equal to 0. We can find out where the velocity changed, and that's going to be important to know. So when t is 2, my velocity changed from negative to positive. So if I go from 0 less than or equal to t less than or equal to 2, I have a negative velocity. Okay? When I go from 2 and make it less than t and make that less than, I don't know, whatever, we'll just say 2 is greater than t. At this point in time, what's happening is my velocities are all going to be positive. Alright, so what's happening is this particle is moving all around right here. And one thing that we need to just kind of talk about real quick is when the particle's derivative is less than 0, it's moving to the left. Okay, what does that mean? That means that if let's look at another graph here. I'm going to graph the derivative this time. We're going to look at the derivative. And it's going to be something like this. This again, this is not going to be perfect, but it's going to be close, pretty close. So we're going to have something like this for a derivative based, based off of our graph. Okay, so as the particle is on this side of the x-axis, we're moving left. And this sounds really weird. It'll get used to it if you'll just relax and just think about it as the particle's just moving. We're just talking about movement, okay? We're not talking about it's following the actual line. And then once the particle hits the x-axis, right here, the velocity is 0. What happens when you have no velocity? You don't move, okay? You could also think of the particle as the particles below the x-axis, think of it as kind of going backwards and slowing down. And then when you hit the x-axis, you're at rest. You're not moving at all. And then when you go across the x-axis, now we're moving forward or to the right. So these are the options that we've got. Well, let's look at our particle down here in this problem. We know from 0 to 2 it's got a negative velocity. That means from 0 to 2 it's also moving left. And notice that the velocity is slowing down. Those y coordinates are getting smaller and smaller and close to 0. And when we get to t equal 2, the particle is resting. The particle is at rest. And then once we're greater than 2, then we're moving to the right. This is really a tough concept to understand, and it's going to take a little bit of practice to actually understand how that thing is moving. But if you've got an x-axis and you look at derivative, anything below the x-axis is going to be backward or left movement. Everything above the x-axis is going to be forward or right movement. And the closer you are to the x-axis, the slower that velocity is. So it'll take a little bit of practice. Again, if you run into a question right now, just please write it down or tweet it so that we've got a record of it and we can talk about it and try and sort out like some of the different things. This can be a little bit confusing, but hang in there and be patient because it will all start to make sense. All right, this is the last slide for this particular section, and when we talk about it, we're talking about marginal cost and marginal revenue, and this all relates to business. You want to run your business in a way that's efficient, and that you're earning money for yourself, and you want to be able to turn a profit. Unlike our federal government, if you don't make money, you can't keep going. And so one of the things that we want to do is make sure that we kind of understand some business basics of this. So we're going to talk about marginal cost and marginal revenue. And marginal cost just simply means looking at the derivative of the cost function, and gee whiz, this thing right here should look really familiar to you by now. We've seen it a ton of times. It's your starting cost and your stopping cost. So, where you stop minus where you start divided by how long it took you to do that. Marginal revenue is the exact same. This equation right here, the exact same equation. The only thing different is the function that you use. If you'll notice in the top we're using a cost function with marginal cost. In the bottom we're using a revenue function, which is marginal revenue. Okay, and so what we want to do is we want to find the marginal cost. I forgot to add that into your notes. So we're going to find marginal cost and marginal revenue as a radiator shop owner, and we crank out about 10 radiators a day. So what we've discovered through running our shop is that the cost to produce 8 to 10 radiators is x cubed minus 6x plus 15. Okay, and the revenue from that is going to be x cubed minus 3x squared plus 12x. And so once we sell the radiators, that's how we know that we've made some money. So we are currently producing 10 radiators a day. Find the marginal revenue and find the marginal cost. We'll do marginal cost first. And so marginal cost just simply means to find the derivative of the cost function. So c prime of x is going to be 3x squared minus 6. Now, what are we working with? We're working with 10 radiators. It tells us that. And so what do we want to do? We just want to know what C prime of 10 is going to be. So that's going to be 3 times 10 squared minus 6, which is 3 times 100 minus 6, which is 300 minus 6, which is 294, if I've done my math correctly. So, right, let's see, 3x squared minus 6, 294. That's my marginal cost, and this is going to be in dollars. Okay, my revenue then, I was double checking in my book, I have a typo. We'll go with what I've got written down. In the book, I think, in the book there is an x right here, and the 6x was squared. So actually, let's just do that. It won't be, it's actually not going to change things too much. So we'll just back up here, new plan, new plan. So that would be minus 12x plus 15. So when I stick a 10 into all those places, I'm going to get, 10 squared is 100, so I'm going to get 300 minus 120 plus 15. 300 minus 120 plus 15 is 195, and we're in dollars here because we're talking about a cost. $195. That's going to be your marginal cost. Okay, marginal revenue then is on the other side of that, marginal revenue, and so we're just looking at the derivative of the revenue function, which is going to be 3x squared minus 6x plus 12. And then I also want to do that guy when we're looking at 10 radiators a day. So 3 times 10 squared minus 6 times 10 plus 12, which is going to be 300 minus 60 plus 12, and on that one I get $252 for marginal revenue. Okay, so there you go, a little marginal cost, marginal revenue. And basically the marginal cost of production is loosely defined, and this is from your book here, to be the extra cost of producing one more unit. Okay, so then your revenue would be tied to that. If we made that one more unit, what would the extra revenue be? So this is an interesting thing to know, because sometimes you can make too many things and not get the revenue that you anticipated because of your costs. So this is an interesting relationship. Okay, so that's it for this section. Again, with this particular slide, if you have a question, you need to write it down so that you can ask or tweet so that we can talk about it.